Hi everyone, are you able to hear me clearly and see the screen clearly? All right, so great, great. Let me just check my connectivity, everything good. All right, so till the last time, what we learned was, okay, so basically we started with the basic understanding of ensembling. The sole idea is to basically pipeline multiple algorithm or same algorithm with different data sets. And we call the algorithms as predictors. So let me just turn on the silence. Okay, so the main idea behind ensembling is to turn on to combine multiple algorithms together or same algorithm with different data set. And this is called, each algorithm we call it as ensemble. We call each algorithm as predictors. All right, that's where we started. We'll talk about these topics. So in general, last time what we proved was that when we have multiple algorithms, then the outcome is generally better than the best. Okay, generally better than the best. Though there are worst case scenarios where the where the number of bad predictors is far more than the good predictors. In those cases, somewhere the outcome lies somewhere in between. Okay, so but in general, the in an ensemble learning, the result of ensemble is better than the best predictor. Okay, so that's what we discussed, and here we tried to show that. Okay, a question from Noor is why one will ensemble same algorithm with different data sets. Okay, so here when you see these predictors, let's say one predictor, two predictor, third predictor, fourth predictor. So we could also have that these predictors are same, but data set is different. Data set on which they are trained, data set on which they are trained are different. Okay, we will when we study the random forest, we will learn that when we study the random forest, we learn that random forest is nothing but many decision trees ensembled. Okay, so question is why same algorithm with different data set? Now, it's a very important question. So each algorithm or each predictor is trained with a different data set. Okay, different data set meaning they behave even though the algorithm is same, the outcome is diverse. Outcome is diverse, and therefore the chances of result being correct is very high. Okay, so let's say there is one decision tree here, another decision tree. This decision tree was from trained on one set of data, one sample, then another one is trained on another sample, and so on. This way, each individual decision tree would behave like a different predictor, and therefore behave as in they will have their diverse predictions. So this would basically give the better outcome. Different sample, yeah, different sample from the same population. Okay, good, very good question. So moving ahead. So Now, we talked about the first classifier as voting classifier, in which what we do is we align the predictors in parallel. We align the predictors in parallel and then either do hard voting or we align the various predictors in parallel and then we either use hard voting or soft voting. Hard voting is like counting of hands, while soft voting is like uh, asking each of them their preference in detail, like asking each of them the the decimal value of each preference, and then summing up these preference, and whosoever wins is the outcome. Okay, after summing up, that's the soft voting. All right, so that's what we further we try to prove that if we have a coin which is slightly biased, meaning let's say there is a coin which is doing some kind of prediction. Biased means a bit of prediction, meaning it's biased towards giving right answer. So if there is a really weak learner which is giving correct answer 51% times, and if you have 1,000 such learners lined up, the the chance of correct answer becomes 75%. Okay, the chance of majority of heads becomes around 75% from 51. So that means that even though individual learner was really weak, like 1% better than the wrong one, as in it was 51% and 49% or less than 50% means it's a random one. So even though individual predictor was weak, it performed, it started giving good results when there were thousands of them. Okay, so that was the answer. So here around 73% is the accuracy of 1,000 coin tosses. Okay, as in the bias, the majority of heads become 73%. That's what we try to prove. Further, we said that when we throw something large number of times, the outcome becomes very much on the lines of probability. That's law of large numbers. Now, we also made our own voting classifier. So we first generated random data like this, and then we took three classifiers. And afterwards, we took three classifiers and then we used them to do the classification. And then we first tried hard voting, and then we tried soft voting. In both the cases, uh, in case of soft voting, the accuracy was 91%, while the accuracy was 89% when using the hard voting. Okay, so soft voting is generally preferred. Now, question you may ask is, when there are hard voting and soft voting is giving great results, then why do we need hard voting at all? Why do we talk about, or why did we discuss hard voting when soft voting always gives good result? Now, the answer is that not all algorithms give you the probability. Some of the algorithms give the answer in terms of yes or no. Okay. In those cases, you don't have an option but to use hard voting as the measure. Okay. So imagine that you are using, say, SVM. So the SVM by default does not give you the probability, and therefore you won't be able to use the soft voting. So, but if you use SVM, you can explicitly say that I need probability, and therefore that then it'll change the algorithms a bit and will give you the probability. Okay, so there are some of the algorithms which can't really give you the probability. In those cases, you will have to use hard voting. Okay, but if your algorithms can give the outcome can give the probability, always use soft voting. Okay, I hope it is really clear to all of you. Yes, Balaji, Bintao, Kamal, Noor, and Ross. Does it sound okay? Right. So any example? Okay. Any example of also which does not give probability? SVM is one. The by default SVM algorithm doesn't give. Then what else? Okay. So as of now, nothing comes to mind, honestly. So, but there could be a scenario where you have trained something with hard voting. You have to train something with hard voting. All right. Great, great. So some of the algorithms don't have the predict underscore probe, and that method could be that method goes missing. So basically, the hard voting classifier generally check for this method in the algorithm and algorithm object, and then take the call. All right. There could be a custom algorithm. That's true. All right. So that was the recap of what we learned earlier about the voting classifiers. All right. Now, okay. A question from Noor is it okay to use ensembling with same algo but different hyperparameters in order to test which one is the best combo? Yes. Um, uh, so we don't, okay. So basically let's say we have an algorithm, we can use different hyperparameters in order to test which one is the best combo. Okay, let me explain. So generally using the CV, the k-fold search, you can generally figure out which hyperparameters are best. So you use those techniques to figure out the hyperparameters. And once you are comfortable with the hyperparameters, when you are happy with the hyperparameters, then you align those ensemble algorithms here. Okay. And then you experiment with different algorithms. Okay. So that is generally the idea. So, but hyperparameter tuning you generally do our using our classic way. Okay. All right. Good. Because here there will be two, three things. Here we are trying to figure out if, let's say, there are n algorithms, and you would like to pick those n algorithms here. So you have, let's say, you want to go with say m choices. So you have actually many permutations to try. And on top of it, if you have hyperparameter as well, then it's going to be little more time consuming. Okay. So hyperparameters, you generally leave it to the usual way of tuning. Okay. And once tuned, then you ensemble them. All right. Now, ensemble methods performs best when a diverse set of classifiers are used. There are two ways in which you can achieve this objective: using different training algorithms or using same training algorithm for every predictor, but train them on different random subsets of the training data. All right, this is what we just talked about. Now, while sampling, so it's very clear that that whatever we do, we would be sampling the data, correct? So when sampling is performed with replacement, this method is called bagging. Okay, so so when you're using different training algorithm, it's not really mandatory to use the different samples. But if you're using the same training algorithms, you would definitely be using different random subsets. Okay. Otherwise, all the algorithms, all the predictors giving the same result, and there is no point of having the diversity. There won't be diversity. Now, so while using the same algorithm or same predictor, you may want to sample, and sampling could be done in many ways. The first one is bagging, as in bootstrap aggregating. Okay, I'm still not very comfortable with the big term called bootstrap aggregating. The the answer is very simple. When you are taking a sample, and before taking uh, another sample, you put the data of the previous sampling back. Okay, then it's called bagging. Okay, so when sampling is performed with replacement, this method is called bagging. Okay, so before taking the next sample, you put the previous sample back. That is bagging, which means there will be common things amongst different samples. Let's say this is your original data set and it has say two blue. Okay, so bag one and bag two might have two blues. Okay, so this is called bagging. All right, now I hope this is clear to everyone. What is bagging? So all right, so the other idea is pasting. Pasting is like cut pasting. We took out, but we did not put it back. Okay, before taking another sample. So when sampling is performed without replacement, it is called pasting. Okay, so if this was the original data set and we took this sample, the second sample would be from the remaining part. Okay, so let's say here we took 4 red and 2 blue. We left with 3 whites. Out of 3 whites, we took 2 in the second bag. Okay, so in case of pasting, the two bags, the two samples will not have repeated data. While in case of bagging, the two bags, the two samples could have repetitions. Okay, repetition is as in there will be common between the two bags. Okay, so both bagging and pasting allow training instances to be sampled several times across multiple predictors, but only bagging allows training instances to be sampled several times for the same predictor. Okay, so imagine that you have the training set like this, and here is the random sampling. The way we the term which we'll be using is bootstrap equals to true if you want to enable the replacement. Okay, so here we'll be sampling either with bootstrap or without bootstrap, and then sending it to predictors and then use that. All right, so once all predictors are trained, the ensemble can make the prediction for a new instance by simply aggregating the predictors of all the predictors, aggregating the predictions of all the predictors, and that's all. Now, the aggregation function is typically either statistical mod or the average for regression. Okay, if we are going for hard voting kind of classifier, then we generally take statistical mode. Okay, meaning we pick the most frequent prediction. All right, so Now, let's compare the two approaches. One is bagging and other is pasting. Okay, so now the advantage of bagging is that, as in, that's an advantage of okay. So so a complex algorithm versus ensemble, generally the advantage is that in ensemble you can use multi-cores, while the individual algorithm may not run parallelly, right? Therefore, therefore, mostly the ensemble algorithms are generally faster. Okay, generally faster because y- more accurate, and ensembling generally gives you better results. So what you do is you basically train all the algorithms in parallel and also use their predictions in parallel and then aggregate the value. That way, if one algorithm is using 1 second and you have four processors and uh, you have four processors and you're ensembling four algorithms, still the outcome will be the same. 1 second. All right. So so even though you improve the efficiency, but your time is still the same if you have four processors and you're using four algorithms in parallel. All right. So so predictors in bagging or pasting both can be trained in parallel via different CPU cores or even different servers. Similarly, predictions from both can be made in parallel. This is one of the reasons why bagging or pasting form of ensembling are very, very important and very useful. They scale very well. Okay. They scale very well. So So Scikit-learn offers a simple API for both bagging and pasting with bagging classifier class or bagging regression for regression. Okay. Now let's try to do that. And let's say we have 500 decision trees, each trained on 100 training instances, random with replacement. This is called bagging. All you want to do is, in case you want pasting, you can just set bootstrap equals false. Okay. Now in this, so so by the basically the parameter that we are going to pass in the classifier, whether voting classifier or in voting classifier, we could say voting the voting equals to soft or hard, and here bootstrap equals to false. Now, number of job parameter tells scikit-learn the number of CPU cores to use for training and predictions. Okay, by default we should put -1 because that allows scikit-learn to use all available cores. All right, we're going to talk about it, Kamals, very soon. Okay, so now let's try to look at it. Let's try to look at it. Okay. Okay, let me just open. All right. And let's just finish till here and just say cell run all above. A question from Binta is that what is the estimator here? Why can it have a value of 500? Okay, number of estimators is the same algorithm called decision tree classifier we are using 500 times. Okay, so here I'll just explain. So what we are doing in this code is we are importing the bagging classifier. Okay, then we are saying that import decision tree classifier. Remember decision tree classifier that we studied earlier, in which it will break down the data based on a particular feature into two parts, and it will keep on doing that. Now, here, the bagging classifier is basically taking an object of this classifier and saying use estimators equals 500. Okay, and these many max samples is what it will be picked up from the input data. When we call it on fit, we're going to pass this data X train and Y train. This is our input data and input instances, and this is our target. Now, when we say max samples, that means it'll, while picking the data from X train, it'll pick about 100 instances. Okay, and we'll feed each of those 100 instances to 500 such estimators. All right, so that was all right. Let me just okay, move ahead. So you can see that here this is what we've done. We have taken a decision tree classifier. Let me zoom out. Yeah, and then we have these. So, okay, okay. If you mark it false, it'll be the pasting. Okay, and yes. All right. So we have the So Kamal's question is, if bootstrap equals false, that it may fail because as they may not get many unique data points. That's right. So pasting, if you are doing pasting on smaller data set, you may not get sufficient data for training, and therefore the result may not be great. But but that's exactly the use case of pasting when you have humongous data set, right? So what you do is you create different data sets using different you create many samples using pasting so that your training, even though the different instances of algorithms are being trained on sorry, different algorithms are being trained on different instances, even then we end up looking at the entire data. Okay, so basically, when you have bigger data set, you use pasting. When you have smaller data set, you use bagging. Okay, yes, go ahead, Noor. So here we have done this, and I think this is very clear to you. So now the accuracy is around 0.912. Okay, let me run it. All right. No, actually, the accuracy is 0.92. Interesting. Here we had the, okay, I think it's the same data. It's just that estimators we have increased to 500. Earlier, the accuracy was 0.912. Now it's 0.92. Okay. So yeah. So this is an example of Bootstrap. Now let's try to visualize the classifier, how well they generalize. Okay. here. The individual's accuracy was really bad. The individual's accuracy was, as compared to this one, the individual's accuracy was 0.856, while the accuracy of 500 of such decision trees was 0.92. Okay, now let's try to visualize it. So this is decision tree, and this is decision tree with bagging. All right, a question from Noor. The parameter is max samples, not sample size. So it may mean that sample size can go up to 100, but it can be lesser than 100 if applicable. Yes, that's right. Okay, so it can be lesser than 100 if applicable. That's correct. Okay, so your guess is right. Okay, great, great. A question from Kamal is that I was hoping bagging classifier to give an error when we set bootstrap equals false with more data sets. Okay, with more sets, like our example, we have only 375, so it is creating many bags with 0 sample. Okay, so error as in the outcome would be bad. Let's just see how is the outcome. Okay, it doesn't seem to impact much the outcome. It has gone down actually. Interesting. Interesting. So here we're talking about max sample as 100. So what would have happened is, and how big is the data? Let's just take a look at the data again. Okay, so this is all right. So is there a way to see the bags? I doubt. Let's just see if there is a, okay, this is the estimate. I think this is the one. Estimator samples. Oh, this is the one. These are the estimator samples, as in basically an array of true and falses. So you have to use this to pick up the data. So these are the samples, and for each of the samples, okay, this is very interesting. I'm just trying to answer and understand the internal working of this particular class. Okay, so we have these many records, and let's say we are saying bootstrap equals false. Okay, so here we have bag clf dot. There is estimator feature samples, and probably the last sample would have more falses. correct? Right. Okay. One way would be to count falses and trues in each of these samples. And that way we would know how many of these are okay. So how should I do? For sample and this, for okay, and we say count equals 1, trues equals okay 0 and 1. For I in sample, we could say count plus equals 1, and if I, then trues equal 1, trues plus equal 1, and then we could say print count and trues. Does it make sense? Okay. Now actually this is what I should do. Okay, let's see what happens. Is there an infinite loop in this? I don't see that. Looks like it's just an iteration that's taking too much time. Wow, actually the interesting part is that even when we used even when you used a bootstrap as false, it is still picked 100 records from each sample. This is strange. Out of total 375. Wow. Okay. Okay. Never mind. I think I'll take a look at it. My assumption here was that it was supposed to be picking less number of records in here, which it is not doing. Is there any other way? Never mind. So how do I undo? Okay. All right. So okay. Mhm. Is it turning it off because the total number of uh, total number of instances are really low. And even if, let's say, we have, say, 5 estimators, and we are saying bootstrap equals false, and then we are doing this, okay, we're still picking up 500, still picking all 100. All right, we'll see that why is it happening so. Is there any other way to force it? Okay, never mind. So we'll take a look at the way it is implemented and I'll give an answer. Okay, a question from Noor is get parameters function. Get parameters function is, do you mean the one on each algorithm or on the bagging classifier? Okay, on the bagging classifier, the get parameters would generally would give us this. Okay, so it's giving us all the parameters that it has assumed by default. Okay, so you can take a look at this. Never mind. So we'll just come back to it again. So here we are saying max samples is this much and number of jobs is this much and so on. Okay. So here the important part that we talked about is the how to figure out like how many instances, how many trues were there in each of them, right? I'll just say no, else. Okay. The calculation is correct. It's just the result is strange. So we'll see that why it's happening that way. Okay, going back up and enabling Bootstrap. Okay, and clear the output here. Okay, clear the output, moving down. All right. So, so the predictions of the bagging classifier were these. Let me train it again. Okay. All right. Did we change something? Saying bootstrap equals to true, max samples 500, 500, and so on. And okay, this is where we are. All right. So based on the sampling, sometimes the prediction is actually improving here automatically. Okay. So, all right. So here, basically, this is what we have. All right. While the individual trees accuracy is around 0.856, here it has gone to 0.936. Okay, it has gone to 0.936. All right. Now, so bagging classifier automatically performs soft voting instead of hard voting. If the if if the base classifier, the classifier that we are using is estimating probabilities, then it uses the soft voting, meaning if the prob a function, prob prob the predict underscore prob a is available in the function in the predictor, then it will estimate the probabilities. If any of them does not have the prob a, it will automatically do hard voting. Okay, so basically it examines uh, it examines the algorithm that you're using for this function, and then takes a decision whether to use soft voting or hard voting. Okay, now, so overall, bagging often gives the better results, which explains why it is generally preferred. Pasting is good for large data set. So general thumb rule is, if you have spare time and CPU and your data set is not really big, then you can use to evaluate both bagging and pasting. Okay. All right. As a thumb rule, generally, if our data set is not too big, then we go for bagging. If the data set is really big, we go for pasting. And in case um, you have spare time and spare CPU, then you can try both of them and see which one is performing better. Okay. So okay, now let's take a look at the decision boundary of an ensemble versus decision boundary of a single classifier. All right. A question from Bintao is, what is contour F in plot.contour F? Okay, let's take a look. Is this the one that we are talking about? All right. So we have x1, we are passing it x1, passing it x2, and then we are giving it y prediction, and then we are giving it the alpha. Okay, and then we are giving it the color map, and then we are letting it plot. Okay, we can take a look at the contour map. Okay. So it basically draws the contour map. That's all. Okay. All right. So it's basically for drawing the contours. All right. This is a method that we are using to draw these lines. This one. All right. Great. Great. So So basically, the important part here is that the decision boundary here in case of individual decision tree, when we increase the depth of it, is actually really, really bad. You can see that it is basically doing the overfitting. Okay, so here you can see that it is doing all the overfitting because we have not controlled the decision trees. We have not regularized it. While the decision tree with the bagging looks like this. Okay, the decision tree with the bagging looks like this. Okay, so what we did was we took so many of these such decision trees in parallel. Okay, we took so many 500 of such decision trees in parallel, and we did the prediction for each one, and then after doing the prediction, we drew this graph. Okay, this graph is based on the prediction of 500 such decision trees. Okay, they must be having similar but similar but on different sample of the overall data. Okay, so you can see that the decision tree with the bagging is the decision tree ensembled is giving us far better results than the individual one. Individual one has done the overfitting. All right, good. So basically the you can see clearly that the bagging has solved the problem of even the overfitting by averaging out the behavior of many such decision trees. Okay, so 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 the ensemble's predictions will likely generalize far better than the decision tree's predictions. An ensemble has a comparable bias, but a small variance. Small variance means overfitting. So it has the the bias of ensemble. The predictions are little better, as in the underfitting part is little better, but it is comparable to the individual, but the variance, the overfitting is lesser. Okay, the overfitting is lesser in case of ensembling. So basically, instead of decreasing bias, we basically improve the variance. Okay, again, the two terms that we talk about, bias and variance, are same as underfitting and overfitting. Underfitting leads to bias, while overfitting leads to variance. Okay, so ensemble has same amount of underfitting as the individual ones have, or maybe a little. uh, it has similar, basically a similar underfitting, but the overfitting is lesser. Okay, overfitting is lesser. So this is a very important sentence. So it make is this clear to everybody? What does this sentence mean? The ensemble has comparable bias but a smaller variance. A question from Noor is, we have achieved parallelism in bootstrapping, right? Can it be achieved in non-bootstrap methods where different algorithms are involved? Yes. See, whether it's bagging or pasting, whether we are doing bootstrapping or non-bootstrapping, we can execute the various algorithms of Ensemble in parallel. So, so parallelism, the NCPU, number of CPU parameter, is valid for both. It is valid for both. Okay. All right. Bagging and pasting, in both the cases, you will have the parallelism. The only difference was with respect to the pasting, since in pasting we don't put the data back, since in pasting we do not replace the items that you pick in the first sample. So even if your input data set is really huge, still you can break it down into smaller parts and train different algorithms or same algorithm on those data sets, and then get the results. All right. So parallelism is possible in both. And in case of pasting, it can give us good results even with the very big data. Okay. And as a matter of fact, the p- pasting was actually designed for bigger data sets. Okay. Okay. Even when you have multiple algorithms involved, you can definitely use the parallelism. Yeah. Okay. You can definitely use the parallelism, and number of CPU you can definitely give there. Okay, let's go back there. Let me just go back to the Jupyter notebook and take a look at the voting classifier. Okay, okay. So let me remove this. Okay, so here the voting classifier that we are using, let's take a look at its class. Okay, it has a parameter called number of jobs. Okay, so the number of jobs means this is the unit of parallelism. Okay, if we say a number of jobs equals to -1, then even though the algorithms are different, you'll get the answer. Good. All right. All right. Great. So a couple of things that we learned. One is the pasting is useful when the data is used. Bagging is a general strategy, which is we use often. And next is the ensemble has comparable bias. Okay, but smaller variance. Okay, you want me to explain this part again? So when we ensemble multiple algorithms together, or same algorithm multiple times, if we are ensembling that, so the result we will get will have the same amount of underfitting, right? But overfitting will be less, as shown in this example, right? If let's say we are trying to fit a straight line by the way of uh, say one particular kind of a regression or a classification. I'm just taking an example, and the underfitting as in, let's say, or we are using region tree of one depth. Okay, so region tree of one depth will be really maybe like this. Okay, so if we have that kind of the underfitting part, the ensembling will not improve the underfitting. The results will be similar. Okay, but the overfitting, you can clearly see here, individual decision tree is overfitting, right? And since we are averaging out the values, the overfitting will be kind of resolved by the ensembling. Okay, by the ensembling, you will get smaller bias, sorry, similar bias, but smaller variance. Okay, is it clear? So it makes roughly the same number of errors on the training set, but decision boundary is less regular. All right. All right. With bagging, some instances may be sampled several times for any given predictor, while others may not be this is a very important idea. So when we are bagging, doing the bagging, meaning we are putting the items back and taking it up. So there are some items which never appeared in any of the samples, meaning no algorithm, no predictor saw those. Okay, those are left out. Those are called out of the bag samples. Okay, so the by default, a bagging classifier samples m instances with replacement, where m is the size of the training set. Now, as the size of data input data grows, the ratio of instances which are sampled to the instances which are not sampled are approximately 63%. Okay, there is some formula that I'm yet to figure out how this number came around. So the ratio of instances which are sampled to instances that are not sampled is around 63%. That means about 63% of the training instances are sampled on average for each predictor. So the important part is when the data size grows, there are huge number of instances that could be left out in case of in case of the bagging. Okay, as the size of the data grows, the number of instances that are left out grow grow hugely. Therefore, 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 we can utilize those by testing on those left out ones. Okay, since the predictor never sees the out of bag instances during training, it can be evaluated on these instances without need of separate validation set or cross validation. Okay, so you can evaluate Ensemble itself on the out of bag instances. So let me put it this way again. So when we are doing the bagging, the chance of some elements being left out and not being evaluated at all keep on growing. And instead of worrying about it, we can actually utilize those left out ones as the testing data set. And that's called out of the bag evaluation. Okay, that's called out of the bag evaluation. So in the bagging classifier, what we can do is we can set OOB score equals to true, and and while it does the evaluation, it computes the OOB score, the OOB score, and it gives you those results. Okay, so basically, while it is training, it is also doing the prediction based on the left out instances, and using that, it is calculating the accuracy. So you did not really need to do the prediction on the testing a separate set of data. You used the same left out elements for testing. Okay, so let me just show you this part. Where was it? Yeah, here. So here it is. That's what it means. Okay, so you can see that we are creating a bagging classifier. We are passing the this particular instance of region tree. Then we are telling that we are going to use these many of these region trees, and bootstrap is true. Number of jobs is -1, meaning there'll be as many jobs as number of CPUs. Okay, OOB score is true. So basically, this OOB score equals to true will basically evaluate these decision trees on the out of the bag instances, meaning those instances which were not picked up by anybody. Okay, so you can see that the bagging classifier's OOB score is this. Okay, 0.89. while the bagging classifier's score on the total data is 0.89. Okay, so that's the important part. Okay, actually there is a good amount of randomness here. Okay, now here what we see is okay, the accuracy of the out of the bag score and the accuracy on the prediction is approximately similar. Actually, it's very much similar. So here the accuracy of both the OOB score, as per given by OOB score, as well as accuracy on the predicted values, as in the test, this X test, is actually same. Okay, so you can see that out of the bag evaluation is very much closer to the normal evaluation. Okay, that's the sole idea. Okay. All right. So a question from Binta is, as m grows, the ratio approaches 1 to e to the power minus 1 and this. Okay, I need to take a look at this. I'm not very clear about exact calculation here. Okay, so let me just note down. All right. Okay, a question from Noor is, we are not passing max samples here. That's right. So max sample is taken as 100%. So it's basically still, this is very interesting. So it's basically picking the all of the samples, and still there are some. Okay. So while picking the individual elements, what it is doing is, okay, where was that the code that we wrote earlier? Let's just take a look at it. Yeah, this is the one. Let me just give it a try. What happens here in case of bagging classifier? So yes, here it's picking these many to around 240 by default. Okay. Okay. So by default, it is basically picking up these many samples. All right. So that's about this one. Ideally, the max samples one is means that you are going to pick up all of those. Okay. Okay. So basically, it is picking these many values out of 375 for each of the sample, each of the estimators. Okay. All right. Let's move ahead. So what we see is the overall the the out of the bag evaluation is actually a good indicator of the actual performance. Are all of you getting the same value here and same value here? Okay, run it again. Let me run bootstrap e equals to true. So there's certain amount of randomness involved here and here. So this one is around 0.08. The difference between this and this is around 0.008, right? 0.008. Okay. So, yeah, because we are picking up the randomness there. And if I put max samples equals to zero point 0.5, then it should give us interesting. Now it is overfitting this. Okay, interesting. Earlier in the beginning one, it actually gave very close results. Nevertheless, so the idea is that it is almost similar. The OOB score is almost similar. Okay, it's almost similar. Okay, a question from Kamal is every time we run it, it's giving different answer. Is there a way to fix it? Yes, the way to fix it is by passing the random number as 42 or some other number. That way, it'll give you that random state equals to say here, right? We could say random state equals to say 42. Okay, now it should give the results every time the same. Okay, so this is the way you could fix it. Now you can see that. Interesting. So just experimenting with it. All right. Okay, so let's move ahead. Try now the random state 42. That one will give you this answer. There's a minor difference between this and this. Is it right now? Try this. Actually, it was 41. I was putting it 41. Good, good. So what we did was we observed that OOB score was actually a very close indicator of the testing. So what we can do is, in case we are using bagging, we can keep the training data as not much required, and that way we don't need to separately test and use the OOB score as a quick validation of how well we are doing with respect to prediction. Okay, so that's a good idea about the out of the bag evaluation. Okay. All right. Now, this is the part we did. Now, the OOP decision function for each training instance is also available through the OOB underscore decision underscore function underscore variable underscore this is the name up to underscore. Okay, so here you can see that this is the OOP decision function, and what it is showing is the um, the result for each of the value. Okay, the result for each of the value. And okay, so here OOB evaluation is estimates that the second training instance has 60.6 probability of belonging to the positive class. Okay, so basically it is actually the two columns are not really required. The OOB decision function is giving you the results about each training instance. First one having 0, and hence of course 1 minus 0 is 1. Then second one is, for it being in the first class, it would be 0.605, and the 1 minus of that one. So basically, so it has the probability of 60.6% to belong to the first class, positive class, and 0.39 to the second class. And so this column is kind of redundant. You can compute this column, second one, using 1 minus 6. So basically, if you want to take a look at the OOP decision function, you could always take a look at this variable. Okay, so let me clear this cell again because it is taking too much space. Okay, so this decision function, and okay, all right, can I do length of this? So there are 375 elements left. Okay, on 375 elements it has done the prediction. Okay, so generally the internal variables end with underscore. Okay. Generally internal variables end with underscore. Okay, so okay, now a question from Noor is, I can't understand the value of OOP thing. Okay, so there were some instances which were left out in case of sampling. That's right. So every time we sample, some instances are left out. And there are basically many such instances. Okay, many such instances that are left out. Okay, so every time you sample it, there will be many instances which will be left out. And using that, you could always do the training. Okay, using that you could always do the training every time. Sorry, you do the prediction and test that, and that's what is out of the bag evaluation is. Okay, should I go back and explain again? A question from Noor is, can this be preferred over proper training data? So practically the out of the bag evaluation is very close to the real predictions. Okay, testing just like you have the cross validation. So the out of the bag evaluation is very much close to the cross validation or the testing on some data set. Therefore, out of the bag evaluation can very well be used to 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 validate your ensemble. Okay. So yes, you can actually to make the whole process faster. Let's say you are doing doing grid search, or you're doing cross validation, or you are trying to do the hyperparameter tuning. So in those most of those cases, you could use the out of the bag evaluation as a very good measure to measure instead of actually testing it. Okay, so out of the bag evaluation is faster than the usual testing because it is done parallelly, while the training is happening itself at that point of time. It keeps on computing the score parallelly, and that way the out of the bag evaluation is a quicker way of uh, of doing the hyperparameter tuning and other parts, or you can say quicker way of doing testing of your algorithm. Okay, but uh, but we'll stick to the testing data as we used in the first project. Okay, all right. Okay, so so this is what we talked about. Let's just move ahead. So the number of elements in that particular decision function were 375. Okay, so so the way I counted is I went here. Okay, so all I did was I did the length of this one. Okay, I did the length of this one, and that gave us the result. Okay, all right, good. Moving on now. A very important idea with respect to the sampling further is the random patches and random subspaces. Okay, so far what we've learned is voting classifier, hard and soft, and then we learned about bagging and pasting. Now let's talk about random patches and random subspaces. The bagging classifier, the class, supports sampling the feature as well. So far, what we did was sample the instances, right? The rows in our data, the rows or instances. We can also sample the features. We can also sample the features. Now, why do we need to sample the features? Sometimes the features are really huge. Remember our MNIST data, the samples were around 784. Sorry, number of features were around 784. Sometimes the number of features are really huge, and that's where we use the sampling of the features. Okay, so sampling of features is basically an interesting part of ensembling. So basically, if you have, let's say, uh, the the input data would have instances. This is our one instance, this is second instance, and these are the features. These are 7 features in this data. Okay, so so the way we did max sampling, in the same way we also do instance sampling. Okay, and okay, going back. So here we are basically trying to sample the features, meaning we'll pick up some of the features, not all. Okay, for training, let's say for training one of the decision trees, we'll pick these features. For training second decision tree, we might pick up another set of features, and that this is called feature sampling. So it works the same way as max samples in the bootstrap, in the usual one. So instead of max samples, we have max feature samples and boot bootstrap samples, bootstrap features. So the way we did row sampling as an instance sampling, we have the same way in the feature sampling. Each predictor is trained on subset of features. Each each predictor is trained on subset of features, is practically useful with high dimensional input. Okay, a question is, how can we sample the feature? Basically, we pick up only few rows, not the other. But how do we decide which feature is important? The answer is we don't. We let the algorithm decide that. Okay, so when you have a really huge set of features, say for example, images, and your algorithms, which are, let's say, which can't handle so many columns, okay, in those cases, using the random subspaces is a good idea. Okay, using feature sampling is a good idea when you are using the input data with so many features, and the algorithm that you're using is taking too much time to handle so many features. Okay, so so sometimes you may want to do both. You may want to do the sampling on instance as well as sampling on the features. This is called random patches. Okay, the random subspaces means sampling only the features, while both the sampling of the instances as well as the features is called random patches. So keeping all the training instances is called the bootstrap equals to false and max samples equals to 1. But the sampling features, we use bootstrap underscore features equals to true, and max features is smaller than 1. Okay, so the max features, the variable has like dual nature. If it is a decimal value, that means it has to be between 0 to 1, and we can control the ratio using the max features. Okay, the same cases with max samples, and this is called random subspaces. A question from Gopi is, can we use PCA to determine which features are important and then perform feature sampling on those? Okay, yes. So a good point. So PCA, the principal component analysis that we are going to do after this, actually deals with figuring out which features are important. Okay, so in case we do not, because PCA itself is a time consuming technique, a bit of time consuming technique. Therefore, sometimes using the random subspaces could help instead of doing PCA, because here we're not caring about which features are important. We are just randomly picking the features, training the algorithm, and picking the average of that. Okay, but in general, if you want to pick which features are important, then we use the principal component analysis. Okay, one a ratio here, yes. Okay, so here if we say max features less than 1, that means we'll pick a fraction of total number of features. Okay, okay, this table would give you a better idea. Now here, if we have pasting, that means max samples were less than 1. Okay, bootstrap was false. Okay, and so we talked about bagging and pasting, right? So for pasting, we did not bootstrap, correct? We said bootstrap equals to false. While the max features were 1, all of the features were picked up. The bootstrap features were false, as in don't bootstrap, And and in case of bagging, we said the total max samples was less than one, while the bootstrapping was true, and we picked up all features. Okay, we picked up all of the features 1.0. Okay, so max underscore samples equals to 1.0 means we want to pick up 100% of instances. Max underscore features means if it is 1, that means you want to pick all of the features. Okay, like in case of bagging and pasting, we did not want to sample the features, right? Therefore, the max features was 1.0. Yes, 1 is a ratio here. Okay, a question is, how do you calculate, and can you give us some example? Yes. So here it essentially means, here lesser than 1 means we are picking up lesser than the total. Okay, lesser than the total. Okay, and 1 means we are picking up all of them. All right. Okay, so a question from Kamal is, in this table both max samples equals to 1 and max features to 1 makes no sense. It does make sense. So actually those are the parts that make sense. So 1.0 means we are picking up all of the features. Here in case of subspaces, we are picking up all of the instances. Okay, so let me go back what we are talking about. So we are ensembling the algorithm together. Let's say we are ensembling same algorithm multiple times. So the sampling could be done in many ways. One was just pick some of the instances, don't put them back. That was pasting. Pick some of the instances and keep on putting them back before taking the another sample. That's called bagging. Then then the subspaces. Subspaces means we pick all of the instances, but only some of the features in each sample. When we are sampling, we are going to take all of the instances, but some of the features. That's called subspaces. But sometimes we may want to do both. We may want to do both, as in you may want to only take fraction of the total instances in a sample, as well as fraction of total features in a sample. Okay, so that's how it is. Okay, a question from Kamal is, it will have no bags then. Um, could you repeat? So basically, the each sample is called as bag. So max samples equals to 1 means we want to pick up all of the instances. And if you want to pick up both max sample as well as max features, then it wouldn't make any sense. Then you're right. Okay. Now I think I got it. You mean that if we have both, then it wouldn't make sense, correct? Essentially, we are not sampling at all. Yes, by default, both values are 1. Okay. So bootstrap means putting the values back before bootstrap means putting the values back, okay, before taking the another one. So bootstrap features basically is generally true. Okay, we actually these parts don't make much of a sense. Okay, these parts don't make much of a sense. Okay, okay. So because bootstrap generally means that we would like to put the feature, put the um, elements back before before picking the next sample. That's what bootstrap is. The difference between bagging and pasting is only this bootstrap. Okay, that's the only difference between the bagging and pasting. Okay, and the difference between subspaces and patches is the 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 max sample that we are picking up. Okay, the max sample that we're picking up. All right. So this table is, yeah, bit of I wanted to just put all the things in perspective. Some of the parameters don't matter to it. Like for example, in subspaces, there is, in both actually, the subspaces and patches, bootstrap doesn't make any sense. Okay, these two columns don't make sense here, two rows, in case of subspaces and patches. Okay, sure. I'll post these slides. I think it will be updated with all of the updated there itself. Okay, I'll just give it to you. Okay. So a question from Noor is, the easiest way should have been a parameter in bagging classifier. Let XYZ have 4 possible values, pasting. Yeah, yeah. Okay, correct. So Binta's question is, there is no such table before. Correct. It wasn't there before. I had updated it. Okay. So as soon as we update, it should reflect on your side. Okay. Good. Good. So basically here we these are the various arguments to the bagging, the classifier, the bagging classifier. If we pass max number of features less than 1, that means we want to do the uh, sampling on the features. Okay, otherwise if we don't pass it at all, it will not sample the features. Okay, similarly, if we don't pass the max samples at all, the this will be the, okay, if we don't want to pass the max samples at all, it will assume these values to be 1. Okay, so this was a quick overview. I hope everybody got it. So is the definition of subspaces clear? Subspaces means we want to just pick the columns, pick fraction of columns. We want to leave some of the columns while training. And patches means we want to do both of it. Okay, so all right. Balaji, Bintao, Gopi, Kamal, Shahrukh, Noor, Prateek, Ross. Okay, all right. A question for Noor is, in patches, bootstrap can be false too. In patches, bootstrap can be false too. Actually, it doesn't make sense here because in case of either patching or subspacing, we are not doing the pasting or bagging. In both subspaces and patches, we're doing mostly the bagging, as in by default, everything is put back. Okay. So it's not like that if we picked a feature, we'll not pick the same feature again in another sample. Okay, that's it. So this is also not valid. A question from Ross is perhaps we need an indicator for incompatible methods. Yes. All right. Okay, great, great. So let me just go back. Okay. So here, coming back to it. Yeah, I think that will be good. I think these are, yeah, okay. This is what I think. All right. Would love to understand, Noor. Let's take a break and we'll clear that up after the break. All right. So I'm back. Should we start now? Hi, everyone. Abhinav, Balaji, Bintao, Gopi, Kamal, Shahrukh, Noor, Prateek, and Ross. Should we start now? All right. Great, great, great to have all of you back. Now, a very, very important topic. So what we have learned so far is that the ensemble trees, ensemble learning is the most practical way of computation. It it basically um, it basically improves your performance and the performance of any algorithm. So most of the winning algorithms across various competitions, you'll find that most of them are ensembled one. Okay, most of them are ensembled one. The other advantage of ensembling is that it makes it possible to it makes it possible to run the algorithm parallelly on multiple machines. Okay, not multiple machines, multiple cores. Okay, so the ensembling gives us good results. It makes it possible to run it parallelly. Also, it lets us handle the bigger amount of data. If you have a huge number of instances, so what you do is you do the pasting. If you have huge number of columns, you do the subspaces. Okay, if you have both, then you do the random patches. Okay, so basically the idea behind ensembling is actually quite practical one, and without even knowing what's going inside an algorithm, you can ensemble them and test for better results. Okay, test for better results. So that's the sole idea. Okay, and what is this image about? Correct, correct. This is one way to present it. All right, good. All right, thank you, Noor. Now, the so ensembling, and in the chapter one, you remember the in end-to-end project, chapter two, the the algorithm that won was a random forest, correct? Algorithm that won was random forest, and random forest is basically an ensembled way. So random forest in an ensemble of is an ensemble of decision trees, generally trained via bagging method. Typically, the max sample size samples is set to the size of the training set. Okay, so basically on the uh, random sample of the input, we train each of the decision tree, and we basically We basically take the result based on the majority vote class. So this is what goes on there. Okay. So we have an instance, we basically have multiple trees and we let them classify and then take the majority vote, and that's a final class. So instead of building a bagging classifier and passing it to decision tree, you can instead use random forest classifier, okay, which is more convenient and optimized for decision trees. Similarly, there is a class called random forest regressor, which basically computes the average of all predictions, and for the class is for regression tasks. Now, let's train a random forest classifier with 500 trees, okay, each limited to maximum 16 node and using all available CPUs. Okay, so here we are saying that from this import this, and then we are saying we're defining this random forest classifier as number of estimators are 500, max nodes are 16, and number of jobs are -1, meaning all available CPUs. So this is the method. Now all we have to do is call fit on this, and then we say predict on that data. Okay, this is the result, and let's take a look at it. All right, so let's go down from here. Let me just clear the current output clear. I think this is better. Okay, so we have okay, so now let's take a look. So here and the prediction accuracy of random forest classifier is approximately 97.6. Okay, prediction accuracy is 97.6. Okay, that's the accuracy. So this is basically the random forest. Okay. A question from Kamal: What is different about random forest classifier than bagging classifier with using decision trees? Not much. We'll see there are some of the algorithms which differ a bit. Okay. There are some more optimizations that are done internally. We'll talk about those soon. A question from Gopi: Is there a way to limit a model from using all CPU cores? Yes. You could just say, is there a way to limit a model from using all CPU cores? So you can always say number of jobs equals to 3. Okay. That means if you have 4 CPUs, if you are quad core, then it'll use only 3. A question from Noor is, what is internal of random forest? Does it do bagging, pasting, patches, or can we control in terms of random forest? Okay, so it does basically the bagging internally. Okay, and we definitely can control the random forest by passing various parameters. So random forest class actually exposes a lot of parameters which have similar meanings. Okay, so let me just show you random. Okay, so this is random forest classifier, and here we have, you can see the max samples, though the methods that we pass to decision trees, those are available here. All right. So you can see that in our usual the in our usual bagging one, the accuracy was around 0.92, but here it's 0.975. Okay, so we'll talk about a bit more in detail, like what goes in random forest. Okay, and there are some more techniques that are being used there. Okay. Okay. A question from Abhinta is, why do you choose 16? Why did we choose 16 here, max 6 leaf? Okay. So max leaf node is this, and okay. Now, basically, these are the hyperparameters. The number of leaf node that we want totally is this. Otherwise, what it'll do is it'll start overfitting it, right? That's why we wanted to underfit. Okay. So basically, it'll stop splitting the nodes as soon as the total number of leaves are 16. Okay. So that's what it'll do. Okay, question from Vidya is, why not 60? Why not 8? You could try both. Okay, 8 becomes just 2 less, or why not 32, for example, right? If it's 32, it's going to take a long time. Okay, now the accuracy is dropped if you have max leaf node as 32. Accuracy is dropped. So basically, it is started to overfit when we have. Okay. So when you keep on bringing it down, then it'll start underfit. Okay. Then also the accuracy is dropping. You can see that. Accuracy is good at this. If we put 8, then let's check the accuracy. Wow. Is it true? The accuracy is 0.99. Wow. Okay. So it's essentially okay. Okay. A question from Gopi is, without plotting, how did we decide on 16? 16 is just one way. As you can see that it's not really optimum one. Okay. And okay. Also, one more thing, when we are saying this, we're comparing at this point of time, we are actually comparing with the bagging classifier. Sorry. So it's actually come here, 97% is actually comparison. Okay. It's actually comparison. I'm really sorry for this. Okay. Here we are actually comparing with the previous predictions. Okay. The predictions, this is random classifier's prediction, and these were the predictions done by bagging classifier. Okay, so when we have max 8 nodes here, then 16 nodes, then the the results are very similar to the bagging classifier. Okay, if we have like 8 leaf node, then it's further similar to the bagging classifier. That's a strange part. Okay, so all right. So basically the results are here. The one that we are showing is the these are the these are the predictions. All right. Okay. All right. We could actually say This is how we test, right? Okay, so the accuracy is 0.92. All right, if I put 32, what happens here? The accuracy drops. Okay, so here basically we're trying to show that how close it is to the random forest. Okay, so you can take a look at this one. If you put it here, this is how it looks like. All right. Okay, so great. So what we just demonstrated is this model is very similar to the backing classifier, the standard one, using the 500, the one that we designed. And so basically, um, the random forest classifier has all the hyperparameters of decision tree classifier. Okay, that means you can control like max number of leaps and other things. So it has some parameters related to the backing classifier to control the ensemble, like how much samples and other things. So now the random forest algorithm introduces extra randomness when growing the trees. Okay, instead of searching for the very best feature when splitting a node, it searches for very best feature amongst a random subset of features. So instead of, so this is a very important part. So you remember how we learned in case of decision trees. So in decision trees, what we did was for every feature, we computed the Gini index, correct? For every feature, we did the Gini index. Now, what does the random forest do? Instead of instead of going over each features and computing Gini index, it introduces a bit of randomness. Okay, it does it over some features, not all features. Okay, this results in greater tree diversity, which once again trades a higher bias for lower variance, generally yielding an overall better model. Okay, so basically, the the more diverse the results are, the better would be the outcome. Correct. So when we have more diverse decision trees, one way is by picking up random samples. The other way is by random, picking up only few features while computing where to split the node. Right? When we in decision trees, what you do is you go over all the instances, you go over all the features. Then for each feature, you compute the where should we split it, and what will be the Gini score, Gini index, and compare all the Gini indexes of all the splits for all the features, right? But instead of that, random forest basically picks up random subset of features and then computes the Gini score for each of these features. This makes the random forest little faster. It makes random forest faster, as well as it makes random forest more diverse, as in each decision tree would be a little bit more diverse than the other one, and this way the results will be better. Okay, so basically it trades bias for variance. Okay, so it will not underfit, as well as when you have more sub trees, they will act like a regularization, and there will be less of overfitting. Okay, so overall the overall model will be better. All right, Noor, Kamal, and everyone, Ross, Bintao, Balaji, Gopi. A question from Kamal is, in random forest classifier, can I see the prediction and probability of each of the decision tree? Let me see if they provide anything. Let's just take a look. So this is our, what was the classifier's name? This is the random classifier. Okay, let's just take a look. Okay, we have best base estimator. We have estimators. Okay, you can see that. These are the underlying decision trees. Okay, and you can use these decision trees for your, okay, for in individual evaluation. Okay, so you can see that some random state is being passed. All right. So that's how you can take a look at each of the estimators. And feature importances. What else? The question was, can we see the predictions of each ones? Okay. So there is probability, there is, okay, score, score. So let's just take a look at base estimator, bootstrap, classes. Okay. The question is, can we see the accuracy of each one? What we can do actually is what we can do is here, decision tree we have, right? Uh, sorry, we have these estimators, correct? So these estimators, we could just iterate over these estimators. So we could say for E in estimators and do the predictions. So you could say E dot predict and then do the computation, right? Like this. Okay. This could be one way to see the accuracy of each of them. All right. Okay, so this is a quick way to take a look. All right. So this is good. So this way you could take a look at it. And so I think, yeah, I think it does the hard voting. So that's what I was seeing. And probably it will be providing that. Okay. So what was the name? Let me just take a look at this. If it is okay. Okay. I think it would be using the hard voting. That's what it said earlier. Let me just take a look at it. Okay, so it does is I think it'll be using, no, it'll be using the, logically it should be using soft voting, but I somewhere read it uses the hard voting. Okay, so logically it should be using the, yeah. will be using the soft voting. Okay, so we'll just have to take a look at later. Logically, it should be, my guess is that it should be using soft voting. We'll have to take a look. I'll just make a note of it. Okay. Does random forest use the soft voting? Okay, so it would be using soft voting most likely based on this. Wonderful, wonderful. So basically, it introduces a bit of more randomness, which gives us better results. Okay, and a question from Bintao is, how can you make tab work for you to have more options? Okay, like when I say random this, I put dot and press one tab, only one tab. Okay, then I get these lists. Okay, now again, could put dot and it'll give you the list of variables. Okay, I hope that's what you're looking for. How can you make tab work for you to have more options? I'm actually also not too used to the tab thing, though I was very used to the tab thing when I was coding in Java. Okay, but for Bintao, it only moves to the right side. Okay. Try the Chrome. Does it happen? Does anybody else face this problem? That the tab, instead of auto completing, it just shows this uh, space. Are we talking about the in CloudX Lab? Does it happen? Okay. Let me take a look at it in your account. Then I'll get a clarity. All right. Okay. Let me just make a note of it so that I can remember. All right. Wonderful. Wonderful set of questions. So question from Noor is, so we can conclude RF is one of the best to go for many cases. Yes, RF random forest is a very good candidate for many use cases. Again, let the grid search speak the truth. And okay, so and we should not underfit our mental model for with respect to the algorithms. Okay, so we would, whatever is the scenario, we'll just follow the grid search and cross validation. Okay, wonderful. Okay, a question from Kamal is, how do we use out of the bag option in random forest? You can basically say out of bag equals to true, and it'll basically keep the OOB score ready for you. Okay, so that also is a good option. All right, it should be there, right? Random forest. Then we have, do we have OOB score somewhere? Yes. Okay, OOB score is false. So all we need to do is, while we were training this, we could say here OOB underscore score equals true. And so we could use the OOB score. Okay. All right. So this way you could actually do the computation of score. So you don't need to really test later on. Now, in random forests, we have something called extra trees. Okay, when you are growing a tree in a random forest, at each node, only a random subset of features is considered, and It is possible to make trees further more random by using random threshold for each of the feature rather than searching for the best possible thresholds. Okay, like regular decision trees do. Okay, now coming back to this. So what does it mean? So remember, we did the Gini index, we did the computation of Gini index, and all we did was we basically went through each feature, and for each feature we did we assumed a position. Let's split it here, then computed left and right, added them together, and that was our Gini score. So Gini score for each split for each of the feature is what we do in case of uh, decision tree. But in case of ensemble, we want to do a more diverse trees. We want to do more diverse. One of the one of the techniques for making it diverse was picking up random samples. Second was random features. Third is that while computing the Gini score, we we choose a random threshold for each of the feature rather than searching for the best possible thresholds. Okay, instead of so we can basically make it further random by choosing different thresholds. So a forest of such extremely random trees is simply called extremely randomized trees as ensemble, or we call them extra trees for short. Okay, once again, this this trades more bias for a lower variance. Okay, meaning we are choosing the we are going away from underfitting towards a bit more of towards more overfitting. Okay, it also makes extra trees much faster to train than regular random forest, since finding the best possible threshold for each feature at every node is one of the most time-consuming tasks of growing a tree. So when we are growing a tree or splitting a node, so it basically computation of gene index is what it takes a lot of time, and compare and finding the best possible threshold for each feature at every node is um, is something that takes more time, right? So basically, instead of iterating over every split, in, so one way is that we pick a feature. Let's say there are k features, n features. We pick a feature from the whole list, and then for each of the feature, instead of computing the gene index of all of the splits, what you do is the moment you reach a certain threshold of gene index, you stop. Okay, this is very similar to what we used to call early stopping. So it's basically we just choose a random good threshold and let it stop at that point of time. Okay, so that introduces a bit of more randomness, is called extra tree. Okay, now this okay, so a question from Gopi. One, is extra tree an advanced version of random forest tree? Yes. Would you ever use standard random forest if you can use extra trees? If you can get enough accuracy from standard random forest, would extra tree be overkill? So in case your number of instances are high, okay, number of instances are high, then extra tree could be faster than our random forest. Okay, and okay, so that way. Okay, a question from Bindoy. What does threshold refer to here? So when we do, where you remember when we were doing the decision tree, so at every point, what we will do is we will split the data, right? And compute the left and the right, the score of the left, score of the right, and then compute the sum and then compare with the other split. And this way, we will choose the split which is giving us best result, right? So instead of scanning through all possibilities, you decide upon a threshold and stop as soon as you get the value higher than the threshold. Okay, so that value is, I think, some random number is chosen, and based on that, it basically picks it. Okay, just trial and error. All right. So Kamal's question is, I really do not see the value of choosing random threshold for each feature rather than searching for the best possible threshold. So basically the idea is that one, it will introduce more diversity in making the trees. Second, it introduces it makes it faster. It makes it faster. All right. So let me just try to execute this. Okay, so we have talked about all of this part. So here we are. Okay, so these predicted trees, these predictions are very similar to the extra trees, our usual one, right? Our addition trees, they're very similar to that. Okay, okay, now, all right. Okay, Kamal's question is, this seems like to enforce diversity, you are not giving importance of merit. Yes, so because, yeah, this is very similar to the organization. So in an organization, the chances are that the, okay, so yeah, the team formation is one such thing that there'll be all diverse kind of people in the team. And the assumption is similar like Ensemble, that you have many people in the team, even if some of them are really bad engineers, still the overall outcome could be great. Okay, so yes, that's a good example of Ensemble. All right, so you can see that the predicted extra trees are very similar to, the outcome is very similar to our standard one. All right, so we could actually compare extra tree with the random forest and then see how well it's doing against random forest. And that way we would be able to judge it better. So we have, essentially we have one more candidate for being used for being used in the grid search. Okay, now feature importance. Important features are likely to appear closer to the root of the tree. Okay, this is a very important aspect. So other than figuring out the predictions, we can also figure out which features are more important than the others. If you want to take a look at our data and we would like to see, okay, which features, which columns are more important than others, then we could use random forest for the same thing, or decision trees can also be used for the same thing. In a decision tree or in a random forest, the features that appear closer to the root at the top level, the features that appear closer to the root are generally the more important features. Okay, the features which appear towards the bottom, they are less important features, right? So the unimportant features will often appear closer to the leaves, or they will not appear at all, right? So here, the petal length is the feature on the basis of which we have splitted this node. And here is the petal width. Okay, now you can see that petal length and petal width are the important features. Most important one is petal length. And second one is petal width, while the sepal length and sepal width is not that important. Okay, So it is possible to get an estimate of feature importances by computing the average depth at which it appears across the tree in the forest, and scikit-learn computes this automatically for every feature after training. Okay, so you can access the results of feature importances variable. Okay, you can access this using feature importance variable. Okay, so these are the feature importances. Okay, so we could say, what was that? Iris targets, iris. This is right, right? No. Oh, iris is not defined. Okay, no worries. So we'll just take a look at it. Now, moving ahead, and so let's take a look at feature importances. So here we are saying get the data set, load iris, and here we are creating random classifier. And once we have fitted it, we can the compute the score. Okay, so you can see that sepal length is this important and petal length is this important. So you can clearly see petal length is most important, petal width is most important, petal sepal length is then third most important, and sepal width is least important of all. Okay, all right. A question from Noor: can you enforce the feature importance? No. Here the feature importance is derived by the system, right? And and therefore it basically, the feature importance is basically computed by the decision tree while it is splitting the nodes and doing various indexes, gene index. So that way feature importances are derived. Okay, so okay, question from Gopi is, can we say that in the case of iris, as there are not many feature, even though petal width is not important than more, not as important as petal length. Petal width is critical in distinguishing between versicolor and virginica. Okay, that's very right. That's very right. That's very right. So basically, the point that Gopi is making is that even though the the petal width is not as important as petal length is, but to distinguish between the two categories, it is very important, right? So the importance, though feature importance looks like really, really cool, but but sometimes the way we look at feature importances may vary. Okay, one of the ways of looking at it is that feature importance should a feature, a particular feature is important because it's helping us to distinguish between two classes. Okay, so yes, you are right. A question from Kamal: this is a cool idea. The data speaks what is important. Yes, feature importance is really useful in many cases. As we will do the principal component analysis afterwards, you will see that feature importance plays a big role in many things. So you can see that the sepal width is actually quite low. Okay, so we can actually, even if we don't have sepal width in the data, we can live without it. Okay, we can still classify the flowers. uh, we can still classify the based on the petal and sepal length. Okay, okay, a question from Noor: so maybe indirectly by adding more data. Yes. Okay, A question from Kamal is maybe by removing sepal width will give us a better classification. Not much actually. It still matters here. It would not get better. I think it'll be the similar. I think it'll be the similar. It would not. The only thing it would give us is make the overall process faster because we have reduced one feature. Hmm. So question from Kamal is, can there be a case where removing a feature gives better results? Okay. So removing a feature means setting the weight to 0. Okay. And most of the trainings, if they are happening properly, they will basically set the weight to that feature at 0. So that will be equivalent of not having that feature at all. But yes, if you have noisy data, the chance of getting outcome could be less. If you remove the noise specifically, sometimes you could get better results. Okay. So sometimes, yes, it could give better results by removing. So I do agree with you. Okay. If we are able to figure out that this feature is not that important, not important at all, instead this feature is basically a random number, then removing it would generally give a better results. Okay. All right. Great. Yes, your understanding is right, Noor. What I understand is in this case, majority is very well classified by using petal width and petal length, but for some or few, it will require sepal features to classify correctly. That's correct. Okay. So with petal length, petal width, you could get say 90% of accuracy, but if you want to go beyond it, you might need these. Okay. Great. So, all right. Great. Now, let's just draw the diagram. Okay. All right. Now, if we do the same thing, if we do the same thing with MNIST data, is it the MNIST data? No. Okay. If you do the same thing for MNIST data, let me just do it for MNIST data, and we plot it. Okay. You can see that. These are the of feature importances of the MNIST data. Remember our digits? So you can see that the one that are white, that means those features are most important, and the one that are black, which are not important, which means the pixels here did not have any impact at all. While this pixel has the most important, this pixel, and this pixel has the highest amount of impact. Okay, so you can see very clearly the meaning of the feature importance. A question from Intao: when I run the code, the plt.figure, okay, let me just see, plt.figure, okay, and figure size this. This RMS is saying index is, okay, okay. Did we change something there? Just run everything from the top till here, and I think that'll be good. Okay, for me, it seems to be working. Just do a git pull and you should get a latest repository. Okay. All right. Great. Great. So you see that these images, these pixels are very important, while these pixels are somewhat important, and these pixels are also important, and but these pixels are not at all important. Okay, so this was the idea of feature importance. Yeah, this is on full data. This is not full data. This is basically on training data. Okay, while it does the training, it keeps updating the feature importances. Okay, let's just see on what did we train it. Go up so we can see here we have done the, yeah, I did it on full data actually. You're right. Okay, great, great. Uh, so further, there is an idea called boosting in ensembles. Okay, the originally was called hypothesis boosting. It refers to any ensemble method that can combine several weak learners into a strong learner. Okay, so basically, by sequentially combining, boosting is about doing it sequentially, while the bagging was about parallel. Okay, so far what we have done is we have created an ensemble by ensembling algorithms in parallel. But boosting is about doing it sequentially. Okay, so originally it was called hypothesis boosting. It refers to any ensemble method that can combine several weak learners into a strong learner. The general idea of most boosting methods is to train predictors sequentially. The output of one predictor goes to as input to another predictor and so on. Though it can't really use multiple CPUs, but it generally gives better results. So training predictors sequentially is called boosting, each trying to correct its predecessors. Okay, so there are many boosting methods available, and most popular ones are Adaboost and Gradient Boost. Adaboost means adaptive boost, adaptive boosting, and gradient boosting is similar to uh, not gradient boosting is not like gradient descent. It is basically boosting the deltas of the results. Okay, a question from Noor. Maybe this is also used to remove background from pictures. Yes. Okay, but the but the output is aggregator. How can it be? Can it be input to another estimator? Okay, so that's what we are going to talk about. A question from Gopi is, what is your view over XGBoost over Adaboost? XGBoost is doing really good. Okay, so we'll just, I have a plan to put XGBoost also, XGBoost also in the extra session. Okay, so XGBoost is doing really good. Okay, so we'll put that. Now, the so in Adaboost, let's start our discussion with Adaboost. So one way for a new predictor to correct its predecessor is to pay a bit more attention to training instances that the predecessors underfitted. Okay, so the in Adaboost, what we do is we do the prediction using one of the predictors or algorithms, and then we observe which of the things are classified or misclassified. Okay, so we run first algorithm, observe what is wrong, what is wrongly classified, and then boost those boost the instances on which the previous algorithm made mistake. Okay, so if a predecessor or previous algorithm did make mistake, then we basically increase the weightage of those instances. Okay, let's take a look at, say, maybe a diagram. Okay, so in case of the Adaboost, what we do is, let's say the same one algorithm is there. So okay, so what we do is we did the fit. Okay, we did the fit, or let me draw this other way. Okay, now here we do the fit. Okay, and we have the model. Okay, once we do the fit, we have the model. Now on this model, what we do is, let's say we do the testing. Okay, we do the testing. I think I'm really bad at this drawing. Okay, we are doing the testing and we are getting some results. Okay, we're getting some results. Now we'll pass this to another algorithm, but before that, what we'll do is we'll do something called boosting. Okay, so this is our, let's say, a decision tree. Okay, just for the sake of it. Then we have another decision tree. Okay, we have another decision tree, and then we have another. Okay, this is not decision tree. This is boosting. Okay, so we, what we did was we did the testing, and in the testing there will be some records, right, where we will be uh, passing this. So what we'll do is we'll basically boost some of the features which are misclassified. Okay, so let's say in this case, when we did the fit, this drawing was classified as 5, while this drawing was classified as 5. Okay, so this one will basically become the input here to this one, and this one also. So we will actually, as part of boosting, since this one is misclassified, we will boost this instance. Okay, we'll boost this instance and decrease the importance of this one for feeding to the next step. Okay, so in case of Adaboost, all we do is we pay more attention to the training instances that the predecessor underfitted or wrongly classified. Okay, so this results in a new predictor focusing on the weakness of the previous one, the new predictor focusing more and more on the hard cases. Okay, this technique is called Adaboost. All right. So the first base classifier, such as a decision tree, is trained and used to make predictions on the training set. The relative weights of misclassified training instances is then increased. The second classifier is trained using the update weights, and again, it makes the predictions on the training set, and then the weights are updated and so on. Okay, so basically the chain continues. The chain continues. First one does the classification and does the prediction. In the prediction, whatever is the wrong. So first one is basically, first we are doing the training, then we are letting it classify, we are checking on which it performed bad. Those instances we are keeping and basically bringing down the index of the other instances. And then on these instances, we are feeding to the next similar classifier and let it do the prediction. So this is what is happening. So first, this was your data. Then first we ran the first classifier, we got some results. At this stage, we also did weight updates based on the results. And then it was fed to the second one, and then again, and so on. The chain continues. So Adaboost is basically chain of predictors. The successors are correcting the predecessors. Okay, predecessor. Successors are correcting the predecessor. Now, the descent boundary of 5 consecutive predictions of the moon's dataset in this example is each predictor is highly regularized SVM classifier than the with with an RBF kernel. So let me go back. Now, okay, a question from Pratik is, how do we test data set? Okay, good point. Question is, once we have prepared this kind of ensemble, then how do we actually check if it is going good? Okay, so basically we call the fit method on all, okay, and take the average of all. We'll talk about it very soon. Okay, now the decent boundaries of 5 consecutive predictors on a Moon's dataset. This is what it is. In this example, each predictor is highly regularized SVM classifier along with an RBF kernel. Okay, so you can see that by the fifth one, it has actually classified it really well. Okay, here you can see that in the beginning it was underfitting, then in the second one it was a little more, and by fourth or fifth it's actually able to classify really well. Okay, so the first classifier gets many instances wrong. You can see that the first one gets many wrong, so their weights gets boosted. The second classifier therefore does a better job on these instances, and so on. Okay, now same sequence of predictors except for learning rate is half. We'll talk about learning rate. Okay, so you can see that there is something called a learning rate. Learning rate is uh, basically while we are applying how much weights do we want to update. Okay, so let's say first one did a mistake, now second one is going to boost some of the instances which are wrongly predicted. The second one is going, so the first predictor is our usual predictor. The output of the predictor goes to a test. Then if in the test whichever instances are wrongly classified, they are boosted or they are emphasized, while the ones that are done and they are doing good, those are ignored. Those are basically the weights are brought down. Okay, so that's what happens. And how much do we want to increase the weights every time is called learning rate. We'll talk about learning rate soon. Okay, so the sequential learning technique has similarity with gradient descent, except that instead of tweaking a single predictor's parameters to minimize the cost function, Adaboost adds predictors to the ensemble. Okay, so what did we do in gradient descent? At every step, whenever our algorithm took a step, at every step, we basically kept on tweaking the individual predictor, right? That's what we did. That's what we did. And in this case, we are basically letting one do the learning and then do the prediction, and then then we improve the previous one's predictions. While in case of gradient descent, we were improving on every step. Okay, on gradient descent, we were improving on every step. Here, we are improving after one predictor has finished the job. Okay, so Adaboost adds predictors to the ensemble and it keeps on making it better. So now, once all predictors are trained, the ensemble makes predictions very much like bagging or pasting, except that predictors have different weights, and depending on the overall accuracy on the weighted training set. Okay, so once the predictors have been trained, right? We have like say 3-4 predictors. Each of them have their own what do you say, weights, and then we have second one, then third one. They all have their own weights. So the ensemble makes predictions very much like bagging or pasting, but the difference is the predictors have different weights, and depending on different weights, which are a function of how accurate each one is. Okay, so uh, we basically pass the input. So I'll come back to this. So it's a sequential learning technique, and it cannot be parallelized. We can only do it partially, some of the functions. Since each predictor can be trained only after previous predictor has been learned and evaluated, okay, as a result, it does not scale well as much as bagging or pasting. Okay, so all right. So here is the answer. So basically, okay, so basically so it basically does the prediction by doing the giving the weights to each predictor and picking the one which is doing good. Okay, so that was all right. A question from Bintao is, what is the learning rate -5? We'll talk about this one soon. Pratik was able to answer your question. How do we test the test data set? We'll show you the formula for the same thing. Okay. There basically we okay. And basically what we do is we give the weightages to every sequence and pick the one accordingly. Okay. And all right, I'll go into more details. I'm not convinced with the details I've given you right now. We will go into more details after this. Okay. A question from when we say adding predictors, what does it mean? Is it adding some penalty term or to correct or that's correct. That's exactly correct, Gopi. Okay, so how can learning rate be negative? I'll talk about this. Okay. Now, so what is the instance? Instance are individual images, right? Whereby we work, we had the classified data already. Now, what we do in this case is instance has features, all right? So first of all, we decide weights. What are these weights? The weights that we are going to multiply each instance with. So a first predictor, the first predictor is trained and its weighted error R1 is computed on the training set. This is how it's going to work. We'll go into this. We will talk about this algorithm if you guys are okay with it in the next session, which is tomorrow at the same time. All right. I look forward to see you tomorrow at the same time. All right. So thank you, everyone. It was great to have all of you in the session. I look forward to see you again. All right. We'll continue the Adaboost algorithm from tomorrow. Okay. Bye, Ross. Have a good day. And thank you, everyone. Keep the session, keep on asking more questions. And yeah, it's okay to have jokes in the class. Uh, yes, I need to check the notifications. Okay, for Gopi. So there was a mistake that the emails did not go to Gopi. I need to take a look into that. Okay. All right. Thank you, everyone. I look forward to see you tomorrow. Bye-bye. And yes, Binta, I'll also look into this. I will try to explain. Okay. Good. Thank you, everyone. I look forward to see you. Bye-bye.